we will move to the next topic, that is thermodynamic process. We will see what is process and what is thermodynamic process. Okay, if you see the definition, process is nothing but change of state. Change of state is known as process, and the series of equilibrium state through which the system passes is known as path of the process. That means here change of state is known as process. We know that state means, in previous example we took the water and that water in one vessel, and we kept that vessel in a fridge so that it will convert it into ice. So we took the water at a state temperature T1 and pressure P1, and when we put this water vessel in the fridge, then we will get ice cubes, so it which having temperature T2 and pressure P2. Okay, and that means that means here at one state we are getting P1 and T1, and in another state we got P2 and T2. For suppose if we plot in PV diagram P and V, we don't know the temperature, but simply we are assuming that at temperature T1, like like P and T, at temperature T1 and at a pressure P1. And next point is, so when ice is melting means that temperature is decreases, so at temperature T2 and at temperature P2. So if we join this 1-2 process, so if we are assuming that every point is in equilibrium state, so if we join these two state points, then so here if we join these two state points, this is nothing but path of the process. If you see the definition also, the series of equilibrium state through which the system passes, which is nothing but path of the process. In this way, path of the process can be defined. And next one is quasi-static process. Quasi means almost. The word quasi-static process means almost. It is a static process. Understood? It is a quasi-static means almost a static process. This quasi-static process, we can say that infinitely very slow process. Infinitely slow process. Okay. Next, coming to the thermodynamic process. Here we studied about what is process. Process means change of state is nothing but process, and if we join this process, it is called as path. And we studied about a quasi-static process. And now we will see thermodynamic process. This thermodynamic process will occur in two ways. One is reversible, another one is irreversible. We know that reversible means, if we take one example, if one person is standing here and he went to some distance here, okay, from here to he walk up to here, so this is the starting position, this is the ending position. So he went from here 1 to 2, and also if he come same path in the same direction to here, then this is said to be reversible process without affecting any system like surrounding, without affecting any surrounding. Then if we come to this initial state, then it is said to be reversible process. Otherwise, if the person is walking from here to here in this one path, from 1 to 2, one person is walking from here to here. So and again this person is if he wants to come again initial state, then he can come in the same direction, or he can come in this direction or this direction. So he coming in other direction, so it is called as irreversible process. Like he did not come in this same path, that is nothing but irreversible process. And also when he is coming from one when he is coming from a second state to first state, like in the same path, but he is disturbing the surrounding. If he is disturbing the surrounding, like a surrounding temperature or pressure, anything is changes in this path, then this process is not said to be reversible process, then it is said to be irreversible process. And these are the causes for the irreversible processes, mainly is because of friction is the main cause of irreversible process. And we can say that frictionless and quasi static process is nothing but reversible process. Like frictionless and plus quasi static process plus frictionless, friction. So frictionless quasi static process is nothing but reversible process. We can, from here we can say that all the reversible processes are quasi static processes, but all quasi static processes need not to be a reversible process. Understood? Because if it is quasi static process, then here friction is allowed, may not be allowed, we don't know. That's why all quasi static process need not to be a reversible process, but all the reversible process have quasi static processes. Okay, I think up to here this concept is clear to everyone. Next we will move to the ideal gas equations. Um, these equations and these formulas, everything is important for competitive exams. Who are preparing for the competitive exams, please listen carefully, and if you want you can write the notes for this. Okay, and this we know that. Okay, firstly we have to know what is ideal gas. Okay, ideal gas means if we take any gas which follows ideal gas equation, then at all pressure and temperature and volume, then that gas is said to be ideal gas. Means if we take any gas, okay, if we take any gas which is this gas has to be satisfy the ideal gas equation. That ideal gas is equation is, we know that PV equal to mRT. If any gas which follow this equation at all pressure, temperature and volume, then that gas is said to be ideal gas. Okay, and here I wrote the ideal gas equation, PV equal to mRT. This is the ideal gas. We know that P is the absolute pressure, which units is kilo pascal, and volume is meter cube, and M is mass kg, and R is the characteristic gas constant, which units is kilojoule per kg Kelvin, and T is the temperature in Kelvin. Okay, in this way the unit C is defined. You have to write these units also. Please be careful while substituting values in these equations. P should be in kilopascal and volume should be in meter cube. Mass is in kg. R is in kilojoule per kg Kelvin. R is T is temperature in Kelvin. Okay, then only you can find the correct answer. And this is the okay, so this is the ideal gas equation. And coming to the number of moles, we know that number of moles is the ratio of mass to the molecular weight. This is the molecular weight. Okay, sorry, here my writing is not that good, please bear with me. And here, from here we can write, here we have mass M. So from here we got M equal to N into capital M. So if we substitute this Nm in this ideal gas equation, then we will get PV equal to N into capital M into RT. So here M is nothing but molecular weight. This is R is nothing but characteristic gas constant. So this M and R both are constant values only. So this Avogadro hypothesis is coming to the existence for this. Okay, so this Avogadro hypothesis, he find the M are equal to some constant. So both are constant values. So which is comes under also constant. So this hypothesis tells us yet particular pressure, temperature and volume, every gas has the same number of moles. Okay, he from this Avogadro hypothesis, he which is concluded that every gas at some particular temperature, pressure, volume, the gas should be having same number of moles, that is 8.314 kilojoule per kilomole Kelvin. Okay, this is the Avogadro hypothesis. So here if we substitute here we got MR equal to 8.34, which is represented as R bar. This constant value MR, which is represented as R bar. So if we substitute this R bar in this ideal gas equation, we will get PV equal to, okay, wait, I will write. So here we got, from here we got PV equal to M into, so we got N into M na? PV equal to N into capital M into R T. So we know that M into R, which is equal to R bar, that is nothing but 8.314 kilojoule per kilomole Kelvin. Okay, here we got PV equal to N into R bar T. So everyone has to write each and every step, then you won't forget. So this is the one formula when the number of moles is given. When the mass is not given and the number of moles is given, you have to use this formula. If mass is given, then you can use this basic ideal gas equation. If the number of moles is given, then you have to use this formula, PV equal to N into R bar T. So here P is pressure in kilopascal, volume in meter cube, and N is the number of moles. R is this constant 8.314 kilojoule per kilomole Kelvin, and T is the temperature in Kelvin. In this way, these two formulas you have to remember while solving the problems. Okay, this is the one formula, and when if they give number of moles, we have to write PV equal to N into R bar T. So which is R bar is nothing but 8.314. Okay, this one you have to remember while solving the problems. Okay, and I will explain some of the values. Okay, I will give one trick here. In problem, we know that normally M into R equal to R bar. We know that this one R bar is nothing but 8.314, which is nothing but kilojoule per kilomole Kelvin. Okay, you write there in your notes clearly. Okay, kilojoule per kilomole Kelvin. If you want to find the R value, then we can write that R equal to R bar by M. M is nothing but molecular weight. If you want to find any gas characteristic constant, we can find with the help of this R bar by M, we can find the R value. For example, if we take air, okay, if we take air, here we know that R bar is nothing but 8.314 and air molecular weight is 29. So from this calculation we will get 0.287 kilojoule per kg Kelvin. So in this way we can find R value when if they ask in exams, we can find in this way. Like I will tell one more example. If you want to find R value for argon, okay, for argon, so we know that R bar by M. With the help of this formula we can find characteristic gas constant of argon value. So from we know that R bar is 8.314 kilojoule per kg Kelvin, and M is molecular weight of argon is 40. So for finding R value, we have to know the molecular weight of every element. Okay, so from this we got 0.208 kilojoule per kg Kelvin. In this way we can find the R value for argon. And if you see for a R value for carbon dioxide, so M is here for carbon dioxide 44, so 8.314 by 44. If we substitute these values here, you will get R value for carbon dioxide as 0.187. In this way you can find R value for any given gas. Okay, and this I will wrap, then you won't get confused. Okay, and one more thing, in competitive exams they used to ask when any gas behave like ideal gas. So we can say that at low pressure and higher temperature, okay, higher temperature the gas behaves like ideal gas. This is the one of the objective question, so you can remember this one. You have to remember this one. Okay, at low pressure and high temperature the gas behaves like ideal gas. Okay, ideal gas, okay, behaves like ideal gas. They may be confused like at high pressure or low temperature, or high pressure high temperature, like this. So you have to remember at low pressure and high temperature any gas behave like ideal gas in this condition. In this way you can remember things. And thank you for watching. If you feel that this lecture is useful to you, please like, share and subscribe to my channel, and you can share to your friends so that they will also get beneficial from this class. Thank you everyone for your support.